Chapter 13, Fluids, Samples. Sample 1. In a vessel, and a liquid container in the rotation uniformly about a vertical axis, show that the free surface of the liquid is a paraboloid, the surface formed by rotation of a parabola about this axis. So we're going to prove it. We have seen the video. Now let's look at the point P. It's in equilibrium. Okay, it's stable. So look at the P. What the motion it is in, it's rotate around this axis with angular velocity omega, right? So it has centripetal acceleration. How many forces act on it? Two. One is the gravitational force mg, and one is the force from the neighbor atoms. We call it tension. Under these two forces, it rotates with a uniform angular velocity. So it has centripetal force m omega squared x, and this force it was offered by F and mg. Okay, and we look at 2-4 along this vertical question. F cosine theta equal to mg. We divide these two, we find sine theta over cosine, the tangent theta, equal to omega squared x over g. So, what is tangent? The tangent mathematically means is dy dx. So we do the integration. Omega squared x dx equal to g dy. We do the integration. So we get y equal to omega squared or 2g x squared. This is parabolic. Sample. A metal rod of length 80 centimeter and mass 1.6 kilogram has a uniform cross-section area 6.0 centimeter square. Due to a non-uniform density, the center of mass rod is 20 centimeter from one end of the rod. For example, like this one. It's not in the center. The rod in water is suspended in a horizontal position by ropes attached on both ends as shown in the figure. Question A. What is the tension in the rope? Definitely these two are not the same. I want to find the one closer to the center of mass and the one is far from the center of mass. Anyway, the tension in two ropes. We look at this one. The center of mass is about 1/3 of this one. And then we have two tension from the rope. Okay? And then we also have buoyant force at the center of this rope. Why it's not here? Because the shape is uniform. Density is not, but the shape is uniform. So the liquid is saying, how do I know your density is not uniform? I see your cross-section is the same, so my buoyant force is in the center. That's the question. So from this kind of a free body diagram, we can find the T. We take, okay, we look at this one, sigma F equal to 0. That means Tn, Tf, Fp equal to mg. Second, we take the torque around A. While we take torque around A, we can just limit this T. So we get counterclockwise, mg half xa. Clockwise, or counterclockwise, half air Fp and air Fp equal to 0. Okay, in these two equations, I get a Tf. Okay, same reason I can find a Tf. And we see this one, the force of buoyant equal to rho Vg, okay? And we find this one. It's very simple. Once you get this one with a TF, TNs, okay? It's a very simple one. The issue of this one is that the buoyant force acting on the center because the cross-section is area, even though the density is not uniform. Sample. In 1654, George, inventor of the air pump, gave a demonstration before the nobleman of the Holy Roman Empire, in which two teams of 8 horses could not pull apart 2 elongated brass hemispheres. These are 2 hemispheres. Inside is vacuum, outside is atmosphere. Question A. Assuming the hemispheres have strong thin wall, so the R in the figure may be considered both the inside and outside radius. That's very thin. Show that the force required to pull apart the hemispheres has magnitude F equal to pi r squared delta P, where delta P is the difference between the pressures outside and inside the sphere. Question B. Taking R as 30 centimeter, the inside pressure as 0.1 atmosphere, and the outside pressure as 1 atmosphere. Find the force magnitude of the teams of horses would have had to exert to pull apart the hemispheres. Question C. Explain why one team of horses could have proved the point just as well if the hemisphere were attached to a sturdy wall. Now let's check the shear. We divided the shear into 2 half shear, okay, because it's half and half. So we want to calculate the force acting to half, okay, by the air pressure. What we do, we divided this half shear into many rings, okay. We take a reference of theta as before. The theta equal to 0 is this ring. Theta equal to half pi is this ring, the maximum, okay? All right. It looks like typical theta at this angle with width d theta. So this is r d theta width. Let's look at the force acting on this ring by air. Okay, it should be perpendicular to this shear, okay, this ring. Okay. And we know the resultant, by symmetry reason, it should line horizontal along this axis. Right? So this force is dF cosine theta. This is theta, this is theta, it's cosine theta. And the total F equal to sigma dF cosine theta, or integration of dF cosine theta. What the dF? dF is the force acting by the air on this ring. That's what equal to the P plus multiplied by air, right? Delta P is the pressure difference. ds is ds, then the cosine. What is ds? The area of this ring. Equal to 2 pi r sine theta, not r. This is r sine, the different radius. Multiplied by r d theta. That's the area of this ring, this. Okay? And then we look at the theta. The theta from 0 to half pi. Okay, so that's the total force. This is very easy. Sine, cosine. Okay, we get this one, very easy one. Okay, delta p pi r squared. It's very funny. This is pi r squared is cross section, the maximum cross section, and delta p is the pressure difference. Okay,